Thanks for your sharing, Mabel. Now, please allow me to introduce our first speaker, Dr. Tim Mollart. Dr. Tim Mollart is the product manager for electronic-grade materials at Element 6, a global leader in synthetic diamonds based in United Kingdom. Dr. Mollart has over 22 years experience in developing synthetic diamonds products for optical, thermal, electrochemical, and sealing applications. The topic of his speech is diamond detectors, synthesis, status, and outlook. Let's warmly welcome Dr. Tim Mollart.
Good afternoon. Welcome to everyone joining this conference. I hope you can see me and hear me okay. I'm in our global headquarters in Oxford this morning, and I'm the only person in the office at all at the moment. Right, okay, I will share my talk. Hopefully you will be able to see this. I will first of all make my presentation live. Share screen. And I'm hopefully going into a slideshow now. Okay, there we are. Okay, well, so good afternoon, everyone. As said, my name is Tim Mollart. I'm from Element 6. And the title of my talk today is Diamond Detectors, the synthesis of them, the status and the outlook. And I hope to explain a little bit about how this very advanced application for diamonds, very demanding application for CVD diamond, has taught us quite a lot about manufacturing diamond that can be applied much more broadly than this sort of narrow field would first suggest. So the content of my talk, in my talk, I will be just talking briefly about diamond synthesis. And then I will be going on to talk about how we engineer diamond for different applications. I'll be outlining a few applications that we have for diamond in those areas. And then I'll go on to be talking about radiation detector materials and how we can make them from polycrystalline diamond and single crystal diamond before drawing my talk to a close. So I think it's worth thinking about that actually, as highlighted by the previous speaker, it's roughly 70 years since groups started researching synthetic diamond, and in fact the actual publication of the Simon Berman phase diagram that led to many of the developments later on. And Element 6 and many other industrial firms are about taking that sort of natural curiosity of a material with all its wide-ranging properties and turning them actually into products and applications. And obviously as Element 6 we have a very much a focus on the industrial applications for CVD diamond, but we're obviously well aware and participate in other markets as well. So as said, 1951, I believe, HPHT diamond was developed, high temperature, high pressure, and as you all know, most of the diamond that's produced by HPHT is 1B type diamond, which has got a large amount of nitrogen in it, and it's possible to make grits, PCD, and monocrystal diamonds. And as you can see, those can be quite large, but effectively there's an awful lot of defects and extended defects in those materials that it's very, very hard to eliminate. And obviously research began in the early, well, really in the 1980s, and research began into what's known as chemical vapor deposition, where effectively you don't work in the actual the right area of the phase diagram, but you're actually taking the surface properties and using atomic hydrogen, you're able to actually grow diamond in the metastable region. And a lot of the work is really focused around actually how you deliver that plasma that disassociates the hydrogen and generates the right growth environment for you, and also and delivering in microwaves, which turned out to be one of the best ways of making that into that resonance chamber, creating the high purity conditions in there and the substrate and growing the diamond on there. And then effectively, there are two materials that we can develop. In the early 90s, people have developed polycrystalline diamond, where you've actually got this sort of randomly orientated crystals that then get a preferred orientation, and they start to grow up and go up into the screen, up into the direction, and they become columnar. And it's very important that after some time of growth, these columnar grains get pretty much parallel, and the grain sizes don't get any larger. At the beginning of growth, you see rapid grain growth, but after some time, you tend to slow down and see these crystals grow up. And this leads to a polycrystalline material with many properties very similar to single crystal diamond. It can have similar optical absorption properties, especially in the infrared. It can have similar thermal conductivity as single crystal diamond, and in some applications it can have sort of enhanced mechanical properties, and it's a little bit easier to dope for electrochemical applications. Single crystal diamond is of course made using a template for growth and using a process which is very similar. And as was said, the first products really started appearing in the early part of 2000, after around about a decade of research and development into those materials. You began to see people establish that they could manufacture single crystal diamond with many of the properties of type 2A diamond. And that's led us into a number of different applications. The first real applications that you saw for diamond were things like optical transmission, and we saw polycrystalline diamond used in lasers, particularly high power lasers for cutting. You're now beginning to see single crystal diamond start to be used in intracavity optics. As we've improved the quality and the size of the crystals available in that area, you're starting to begin to see some applications for high power lasers of single crystal materials. Thermal conductivity has been used in heat spreaders in the semiconductor industry, and again that's used quite commonly in the actual data infrastructure. Possibly today we're using machines that may actually have diamond heat spreaders within them. And you'll certainly start to see a great deal of interest in high power gallium nitride devices, particularly as 5G begins to come online. We also manufacture polycrystalline diamond in the form of a speaker dome that's useful for high quality hi-fi and reproducer. And again, you can buy this in domestic products and also in cars. In sensors, for the last 10 years, we've seen the emergence of quantum devices and quantum optics using diamond. And again, that is enabled by the availability of high purity diamond. And today I will talk quite a bit about using the electronic properties of diamond in radiation detectors and what that teaches us about these materials. And likewise, you can use diamond for water purification and electrolysis applications. It's got many there. And of course, finally, there is a great deal of interest at the moment and focus on lab-grown diamonds using the CVD process. And obviously, as a consequence of the uptake of lab-grown diamonds, Element 6 has been able to build a new factory in Portland, Oregon. That's a state-of-the-art facility, and it's much larger scale than previously seen. And as you can see from these photos taken in late September last year, the building work of that is completed. And whilst Element 6 is a safety-led organization, we are able to continue the process of commissioning this plant during the COVID-19 disruption that we're having. And whilst work has slowed, we are broadly on target to come online in 2020, this year, in fact. So it's a very exciting time at the moment for us. So then the second part of my talk is really about engineering diamond and how you can actually manipulate the properties of it for different applications. And I think that's quite important for a number of different applications. As we all know, diamond can range in colors that's available synthetically. It can range from colorless with low absorption to quite reasonable levels of blues and pinks and other colors. And these are all generally done by manipulating the defects in the diamond. And obviously you have point defects in diamond, such as chemical impurities and dopants substituted into the lattice, such as nitrogen, and it's the nitrogen vacancy complex that gives rise to the quantum optical properties and the pink color. You've also got extended defects such as dislocations and stacking faults, and then these can be quite a problem in CVD diamond because unlike many other semiconductor materials, you can't anneal them afterwards to eliminate fully these extended defects. So the control of those defects in the CVD process is again quite important to getting different properties of it. And then finally, you've got actually the template that you have for growth in single crystal diamond, and that quite a lot of the properties of diamond can actually stem from that substrate that you've grown on. And finally, polycrystalline diamond kind of combines all of these difficulties along with the complexity of grain boundaries. And you can see a lot of different types of extended defect, particularly in diamond, as well as all the point and extended defects that you'd find in single crystal diamond. So in this picture taken of material here, you've got different growth sectors, you've got different uptake of impurities, you've got stacking faults and grain boundaries and strain and voids and many other complexities. So polycrystalline diamond, in a way, is a much more complicated material to think about in some respects. The CVD process, though, unlike HPHD, gives you many more levers in which you can actually manipulate the properties of the diamond. We're able to model the plasma and the gas phase of that plasma to optimize it to couple in as efficiently as possible and engineer how the actual growth species and the temperatures of the gas phase. You can then look at the chemistries themselves of the gases that you put in and try to optimize those to give you the best quality of growth or the highest purity or the fastest growth rates that you're looking to achieve. And you can definitely engineer an awful lot in the chemistry. And then finally, as mentioned, you can look at the substrates and the surface conditions that you get on your plasma, as well as the growth conditions there, and manipulate again that to optimize the growth process. So unlike HPHT, where there are limited ways of controlling the growth process, or certainly in these, you can actually see many more and get more. And as an illustration of that, I wanted to show you just how, by improving the substrate and how you do that, how you can profoundly change the optical properties of diamond. And that obviously, single crystal diamond should not be what's called birefringent. It should be isotropic and have uniform optical properties in all directions. So if you look through the diamond this way, you should see exactly the same as you looking through this way. But it turns out that dislocations that propagate from the substrate themselves and through into the diamond actually profoundly change the strain state of the diamond, which then gives the optical properties some aspect of anisotropy. And you can actually see these defects in the substrates. Equally, you can get them from the substrates, but you can also introduce them during the growth process. And it turns out that when we were engineering diamond in the mid-2000s, laser groups were very keen on using diamond, but they told us that they could not use our diamond because the birefringence was too high. So we set about a research program to look at how we could improve that birefringence, and we did find from X-ray topographies, we could see the defect structures coming through the diamond. You can see them starting at the substrate and propagating through from the substrate. And we found that if we could improve the substrate, we could get those, eliminate those further. And again, if we could then further improve how the interface actually and what was triggered in the interface, we could really minimize those, and we could bring what's called the birefringence down by 2 orders of magnitude. And roughly 10 years after that research work was first published and first seen, and the optical properties were actually demonstrated, we're starting to see the first industrial applications of these as people explore diamond as an intercavity optical device, particularly in higher powers, where they're looking to minimize or improve the heat dissipation in those types of lasers. So finally, I come on to section of my talk about detector grade diamond. And effectively, I'd just like to say that a detector is a very simple electronic device. in that really it consists of a piece of high purity diamond with some electrodes and a bias voltage and some collection electronics. And here's sort of a typical kind of devices it's used. But these have a number of interesting properties that are unique amongst the solid state detector devices. And just sort of to remind everyone how these work, these are worked by the radiation passing through the crystal, generating an electron hole, a charge pair, that then migrate to the anode and the cathode of the electrode. And effectively, you're then able to measure the pulses that are generated by that radiation charge coming through. And you're able you measure the charge collected and the shape of these pulses, and that tells you quite a lot about the radiation that you're examining. The requirements for these type of materials are to kind of minimize the charge that is lost by the particles generating. And if you can do that, there are a number of applications. So the first one is that these are all used in synchrotron radiation sources, which are used for beam positioning. And it's the kind of radiation hardness, the high temperature operation, and the kind of low absorption of the beams that are used in there. The high energy physics community, particle accelerators, CERN, SLAC, and all the others use diamond as part of their timing and safety systems to ensure that the beam is on track. And there is the ability to embed a monitoring system within the actual accelerator itself and leave it there for many, many years, along with the fast readout time. In the Large Hadron Collider, the bunches are around about 15 nanoseconds apart, and they take 100 nanoseconds to complete one lap of the accelerator. And the resolution needed for these devices in order to monitor them and shut the beam down if it's deviating from position require you to have a picosecond response time. You're also beginning to see medical applications for diamond because it has a very good match with human tissue. So particularly in dosimetry, and particularly in kind of proton therapy, which is the very newest form of radiation therapy for treating cancers, they are using diamond as a measure, a way of positioning that beam, and also a way of actually accurately determining the dose of that diamond. And again, it's different applications and different properties that make diamond a compelling case in these kind of applications. Finally, you can use diamond to detect neutrons, and you're starting to see this use at a very exciting period of time as we are building the first prototype fusion nuclear reactor in the world. Again, the high temperature stability and the radiation hardness and the ability to measure the energy of the neutrons generated in fusion plasmas, again, makes diamond a very exciting material in this application space as well. So what kind of materials have we developed? What was our journey that we went on? Well, the first material that we really developed was a polycrystalline detector material. And again, it's interesting to work out how we actually sort of characterize this material. You're using a controlled beta source which has a known charge generated in it. And then you look at that charge that's generated and try to see how much of it you're collecting. And what you find in polycrystalline diamond detectors is that generally they saturate with a certain voltage, and their charge collection efficiency is limited to around about 35 to 50%, i.e. the number of defects in these materials is still there, and that's what we got. We were developing these materials from the very early 1990s onwards, and really what you saw is it took us about 10 years to actually get through to get this optimized material. And what we actually found was that actually as we progressed, as we learned more about it, our purity of material was improving. We were able to get the nitrogen contamination in the materials down quite a long way, and we can actually also improve the extended defects and the grain size of these materials. But we reached a limit in these materials around about 200 microns of charge collection distance, which is around about the grain size of these polycrystalline electronic materials that we could make. And the applications of those came soon after. And the reason is, as I show you in here, is they're used in the beam safety monitoring in particle accelerators. And if I show you here, here's the response. The black line is a response from a silicon diode, and here's the response from a diamond diode. And it's this very fast response time, coupled with its radiation hardness, that enable people to embed the detector within the beamline. This is an accelerator called vapour that's at the Stanford Linear Accelerator Laboratory in California. And this was one of the first beamline monitoring systems that was actually installed, and that was installed back in 2004. And again, these systems are still stably in use now. And as I say, they're used at CERN in all of the detector experiments and also in the accelerator itself. And they've been operating there, I think, for in some cases over 10 years. But as I said, there's limitations to those materials. And the next thing that we really developed was single crystal detector materials. And let's change that. It's supposed to be a growth video. I should see if that works now. No, it's taken the wrong video. I do apologize. Maybe I won't play the video, but the video itself was a single crystal diamond growing in the process itself. And the real advantage of the CVD process is our ability to watch the growth process and really look at the formation of the crystal here and improve the purity. And back in 2002, papers were published that showed for the first time that the CVD diamond process technique could actually really establish what the electronic properties of diamond were, because the natural diamonds that up until that time had been used really didn't show a very good, a true reflection of the optical properties, the electronic properties that diamond had. And what you find is that you need nitrogen to be, I'm sorry, there's a typo here, below 5 parts per billion. There's a typo in here, it's not per million, 5 parts per billion. And you need very low dislocation densities. If you can get them below around about 1 million defects per centimeter squared. And when you do that, you get very high mobilities of electrons and holes in the material, and you have very good insulating properties. And then around about 2007, a very nice experiment came out that really showed the role of nitrogen. This is actually looking at luminescence of a cross-section of diamond, of CVD diamond on a substrate. And what you're looking at here, these are where there are layers of nitrogen dopant introduced at around about 20 to 30 parts per million, parts per billion. And as you can see here, in this is what's called proton IBIC. You're looking at the current imaging from here, and you're seeing 100% charge collection efficiency in the areas where there is no nitrogen, and in the areas where it's even 20 parts per billion of nitrogen, the charge collection efficiency falls right off. And that was very important to being able to go back to our original experiment of taking one of these solid-state ionization devices with a calibrated source, and what you find is single crystal diamond can have almost 100, can have a charge collection distance that is only limited by the size of the sample itself. It's actually rapidly saturated at very low voltages and therefore is constant. So there's very little trapping in this material. And then secondly, when you calculate the charge collected, the charge collection efficiency can be very close to 100%, i.e. for every single particle that is captured and generates a charge within the diamond, you can actually see that charge and collect it and interpret that data. And as I say, the real key to that is the low defect density and also a very low nitrogen content, well below 5 parts per billion. give you context for that, as a type 2A diamond would be considered type 2A if the nitrogen was more like nearly 500 parts per billion. So it is really a very much lower material than you find in most of the lab-grown diamonds that are grown particularly for the jewelry applications. And again, you see here that polycrystalline material, you see the saturation occurring with grain size and voltage. And the key thing that this can now do is that you can now exploit the drift of electrons through the material. And if you use a different radiation source, you can actually look at the energy that it's being produced, because depending on how much energy the radiation has, depends on how far into the diamond it will penetrate before it'll actually generate a charge. And by measuring the drift time through the material and drift velocity, you can actually resolve in single crystal diamond these energy peaks, i.e. you've got a spectrometer capability that you don't have in polycrystalline materials, where you detect the radiation, but you don't know anything about the energy of that. Again, that's been commercialized, particularly in the high energy physics community and also in the neutron community, for actually as a spectrometer devices. You can also use diamond detectors to detect neutrons. Depending on the energy of those neutrons, if they're above 6 MeV, you can actually break the diamond down itself, and you can actually measure the charge that's generated from that. And again, you can use the drift velocity of the electrons and the holes to tell you something about the energy of that neutron. And equally, with lower energy neutrons, you have to use a converter layer that you attach to the diamond that again generates generally an alpha particle and generates hole pairs. And again, you're able to use the drift of those to tell you about the energy of those particles. And finally, as I mentioned, you can also use the fact that diamond has a linear response, single crystal diamond has a linear charge collection efficiency with the thickness of the diamond, and also with the dose. So you can make very thin devices with 4 quadrant electrodes on it, and use that for beam positioning, because essentially when the beam is passing between the middle of these, you minimize the actual current that you're actually generating. And again, it's the fast response, low absorption, and high radiation damage hardness that makes these devices useful. And these are used in all of the research synchrotrons that you find around the world. And finally, something about the production of these devices and how long we've been manufacturing them for. We've now been manufacturing these for well over 10 years. And this is a cross-section of material of detectors. They're all calibrated using a gamma response here. And of the 500 crystals supplied in this particular run, only 4 of them actually had any properties that deviated from what was considered the standard properties for them. So I show you here the 4 that are deviant, and then I show you the rest of 496 samples that all give a pretty constant response. And what's pleasing for element 6 is the fact that it's our ability to manufacture these parts consistently with such high control that we've actually got the defects and the extended defects and the point defects down and under control enough that we can actually manufacture at these scales. So finally, I come to the conclusion of my talk. CVD synthesis has been developing since the late 1980s, and that we've reached a very exciting time as we've got control over purity, we've got control over defects, both point and also extended defects, and now we're really seeing our ability to scale manufacturing and get dedicated plants that are built to produce large volumes of CVD diamond. The electronic properties of diamond are enabled by CVD. CVD enables you to work out, establish what they were, and also able to make products from them and control them. What we found in polycrystalline diamond that you can make ultra fast, high radiation hardness beam timing applications, but they're limited by the extended defects in those materials. They have an important role and they're a niche product. Single crystal CVD diamond detectors give you many advantages, including being able to make these solid state spectrometers and neutron detectors and beam positioning detectors that are both radiation hard, fast, and also have a very stable properties in relationship to temperature. And then finally, it's really very exciting to be able to say that we are able to now produce these materials in sufficient volumes that we can address industrial applications for them. And you're seeing now the emergence of quantum optical materials that are built on this understanding of how to make very high purity diamond and manipulate the defects within it. And that's an area I think that will grow over the next 20 years and perhaps may even supplant these applications that we have for diamond now. So finally, I'd like to acknowledge my colleagues Joe Dodson and Daniel Twitchen for a lot of the data that I used in this talk. I'd also like to acknowledge the company of Cividec Instrumentation, particularly Eric Griesmer and Christina Weiss, who provide some of the data that I used, and also from Micron Semiconductor, Grenell and Amanda Boothby. Okay, so that's really my presentation. I hope that you've enjoyed it, and I'd be happy to take any questions.
Thanks for sharing, Dr. Mollart. It was impressive. Now in my hand, I collected some questions from the audience. We will share it one by one for you. If the audience have more questions, you could click the hand button during the webinar. We will invite you to the front page to speak with the guest speakers. So here comes the first question. Can you, Dr. Mollart, can you please guide your perspective towards lab-grown diamonds in the coming days? Will new generation expect the products? Do you agree that the name of the game is of robability? Hello, Dr. Mollart.
Hi. Yes, I'm here. I'm sorry. I'm not sure I fully understand that question. I mean, as I said,
vulnerability. I'm sorry.
The vulnerabilities. Well, I really come from the industrial side of the business, and I can really reiterate that we see it as a very exciting time, being asked to ramp up our production after 30 years of development of this technology to a scale we feel is of a benefit to the industry, because we think that there's a lot to be done there's many challenges to expanding your production to meet the demand that may come from lab-grown diamonds. So for the last while, I'm afraid we've been very much embedded in delivering that project and that challenge. Say in 2020, we're very excited to announce that our plant is online, and we are actually producing. In terms of the vulnerabilities of the market, I'm not an expert in the lab-grown diamond field, and I'd have to refer you to De Beers and perhaps the Lightbox team, who may be able to tell you more about that.
Okay, thank you, Dr. Mollart. And here the second one. What is the approximate thickness of the single crystal diamonds?
In the application that we make with detectors, generally we make these diamonds around about 0.5 millimeter in thickness for these applications, because actually you find that there's no advantage to making them thicker because they have 100% charge collection efficiency. So essentially, and in fact, in many challenges, the desire is for thinner pieces of diamond to reduce the absorption of the radiation. So generally our electronic grade materials are manufactured to 0.5 millimeter in thickness. Obviously, for industrial applications of other types of diamond, the thickness can be much greater.
Okay, the third one is how to measure nitrogen content in element 6.
Well, there are really two techniques that we use. The first technique that we use is luminescence, using ultraviolet illumination. You can actually see the sort of orange glow from nitrogen, single substitutional nitrogen that's in the diamond, and we find that a very powerful technique that you can use definitely to determine concentrations to around about 2 to 5 to 2 ppb using that techniques, using such as an instrument such as a diamond view instrument. You can then also use the quantum optical properties, and you can also use what's called EPR, or electron spin resonance, and that has a sensitivity to less than 1 part per billion to nitrogen, single substitutional nitrogen.
Thank you, Dr. Mollart. Here comes the fourth one. What did you mean when referring to the converter layer in blue on slide 32?
Sorry, on slide 32, what did I mean? Let's go back and have a look. Oh, yeah, so what I mean by a converter layer in these materials is where you add a layer that will absorb neutrons and then actually translate that into an alpha particle. And you do this when the energy of the neutron is so low that it would normally just pass straight through the diamond without it being detected. So essentially what you're doing is, if you put, say, a lithium layer on here, when the neutron encounters the lithium-6 ion, it actually produces an alpha particle, which then passes into the diamond, and you're then able to measure the response of that alpha particle. But because you know how the characteristics of the converter layer, you can then translate that into the actual properties of the neutron itself. Does hopefully that answers the question.
Okay, thank you, Dr. Mollart. Here the fifth one. What is the method to convert birefringence image to numerical result regarding to the dislocation defect density?
Not sure I fully understood the question, but essentially what we found is that you need the defect density in the material to be below around about 1 × 10⁶ defects per centimeter squared, and typically and you also, as I say, need the point defects to be really below 2 parts per billion for these electronic applications. So those are both very stringent requirements, and when you don't get those either of those right, you can lose the spectrographic capability that diamond has, and it's useful, and its single crystal diamond has, and it's used as a spectrometer material. So essentially, when defects are above that 10⁸, 10⁹ defects per centimeter squared, then again you start to see properties which are more similar to the polycrystalline materials that we've already developed.
Thank you, Dr. Mollart. Here the sixth one. What is the advantage and the disadvantage of MPCVD to grow? I'm sorry, I will repeat that. What is the advantage and the disadvantage of the MPCVD to grow polycrystalline diamonds? Thank you.
Well, I think I'll come to sort of couple of points here. The advantage is that it gives you very high control over the purity of the diamond that you're producing, and for some applications, even in polycrystalline diamond, that is actually very important. And I think the advantage, as sort of the schematic for our reactor would show you, that essentially it's the fact that it's electrodeless. So essentially, you can reduce the contamination that you get from other types of discharge system, and also, as I say, because also the intensity of the plasma gives you access to a greater range of plasma chemistries than you would otherwise have. So particularly when you're trying to produce materials with high with high phase purity, or with you're engineering material for high thermal conductivity, for high optical transparency, or for high boron content, it can be very useful to be able to manipulate and access other areas of the chemistries that other types of CVD process find difficult to access, particularly, for example, hot filament growth technique, which really limits the temperature of the plasma and thus limits the chemistries that you actually can see. Okay.
Thank you, Dr. Mollart. Here comes the 7th. How to grow high quality heat spreader.
Well, again, that's at the moment those products are polycrystalline diamond, because you a bit like I showed you with the electronic properties of diamond, the thermal properties have a similar characteristic about them. And essentially, by controlling the grain boundaries that you have in the material, and by controlling the phase purity in those grain boundaries, you can actually achieve thermal conductivities in excess of 2,200 watts per meter per Kelvin in those materials, pretty much in a similar way that you can achieve the high electronic properties by really controlling the defects. So we go about that process by looking to grow material, control the morphology of that material, the grain size and the grain structure, and grow these large columnar grains with grain sizes up above 200 microns in size. And then we can start to achieve the kind of properties, high thermal conductivity properties, which are desirable for a heat spreader.
Thank you, Dr. Mollart. Here's the question 8. For the application of neutron detectors, specifically for word energy neutron detection, what performance can be achieved? Thank you.
I think I'm going to have to probably take that question offline to get the specific answers to those questions, because, as I say, many of these devices are made by other companies, not Element 6 itself, and I'm reluctant to jump in with the properties and the energy resolution. But I do know that neutron devices are manufactured, and they do have reasonably good energy resolution. I'll take that question offline, if that's all right.
Thank you, Dr. Mollart. Here is the question 9. What kind of MPCVD does E6 use? Does MW come from above or below? Which design is more efficient in your opinion? Thank you.
Right. Again, well, I think I come back to a picture of a schematic of a reactor, essentially, Element 6 manufactures its own synthesis technology. We do not use third parties to design our reactor or our cavity. And as the questioner would say, we would argue that indeed it is important to design that. But as you can probably understand, I'm reluctant to divulge much about our own technology that we use. It has been in development for over 30 years, and key to it is trying to make the device as efficiently couple into the plasma as possible. And I'm afraid I don't think I can really go on to compare different our devices to others and how they work.
Thank you, Dr. Mollart. Here is the question 10. What is the M in the chart on the right on slide 39? Thank you.
What is the what? The M.
What is the M in the chart on the right on the slide 39? M.
I think it's oh, I see. It's here. It's essentially, I think it's some sort of radical. It's just to convert from a methyl radical to a acetylene type radical. So I believe that M is just saying it's just a methyl radical of some sort in that chemistry.
Thank you, Dr. Mollart. Here is question 11. Does the MPCVD diagram in the slide 39 is used in E6? Thank you.
Well, as I say, as you can look on our website and download our CVD handbook, we've always felt it's important to explain to the wider industry how diamond is manufactured. We think one of the big challenges to the use of diamond outside jewelry, if you like, is actually an awareness of what this material is and how it's manufactured and what it can be used for amongst the wider industrial community. You can ask an engineer in a telecoms company, they know anything about diamond, and apart from the usual things, they probably aren't aware of its industrial uses and its industrial properties. So we put out a diagram that explains to people the fundamentals of how you grow diamond. And we would say that our reactor this diagram is accurate in that it says we do use the microwave CVD process. We do actually couple into our chamber via a waveguide and an antenna system. We do use a window to actually make our vacuum chamber integral. And then we do grow on a substrate in a resonance cavity. And we do that because we like to explain to people why the size of polycrystalline diamond is limited to around about 6 inches, and that actually the microwaves that you need to generate, of a certain frequency, a heating frequency, to actually do that, and that we also try to explain that it's a very power dense process. So the cost of manufacturing diamond is kind of related to the consumable costs of power, and the capital equipment is actually unique to manufacture it. So again, those are components into the cost. So we have this diagram to explain to customers, to raise awareness of how it is. But is this a precise recreation? Well, it's a cartoon version of our reactor technology.
Thank you, Dr. Mollart. Here is the question 12. Do you think the reactive species for the growth of CH3 or C2H2? Thank you.
I think that that the growth of the diamond predominantly comes from the C2. It plays an important role, and I think there's a lot of modelling work around that talks about how the surface plays a role and the chemistry plays a significant role in this. As you can see in the model here, we show the methyl radical as being sort of high importance, but you also, obviously in the growth process, you're getting an awful lot of the C2 type radical in the growth, and that is an important part of the CVD growth process.
Thank you, Dr. Mollart. Here is the question 14. Oh, I'm sorry, it's 13. Does CVD diamond has low carbon footprint compared to the HPHT diamonds? Thank you.
Well, again, taking that back technically, it depends on the source of the power that you use to generate the plasma. So it's certainly true that a great deal of the cost of manufacturing CVD diamond is through the energy consumption to break up the hydrogen molecule and make the hydrogen radical that you need to drive the growth, the CVD diamond growth process. And how green your technology is really depends on where you're located in the world, because you're using a considerable amount of electrical power to drive this process. Here in the UK, I believe the kind of non-fossil fuel contribution is around about 30% of our power at the moment, which is growing. But obviously in Portland, Oregon, that's an area where there is a great deal of hydroelectric power generated. And our plant in Portland, obviously the carbon footprint of our plant in Portland is very much lower than other parts of the world, because the proportion of power that is generated via green means is very, very high in the Oregon region.
You are entering the meeting now.
Sorry.
Thank you, Dr. Mollart.
Yeah.
We learned a lot from your answers. For the time limitation, we will leave the rest of the questions to the Q&A part. So yeah, wait for your question. And we will, if you can click the hands button that you can speak with the speakers. Thanks for sharing, Dr. Mollart. It was very impressive. Thank you.
Okay, thank you. I shall try and stop sharing my screen, and I shall return to hiding away. Okay, thank you very much for listening.
Thank you so much, Dr. Mollart. We learned a lot from your speech. It was impressive.
Okay.